I've been counting down the days to get out. I've been looking for a way from this town. And you're too far away to help me now.
Okay, welcome back to this next part of this live stream of coding up the LDSO Twitch version. In the last part, we have left off at the FullSystem.cc file, so we will continue here. And we have finished the method called makeKeyFrame, which takes in a frame hashing and initializes the frame and does some preparational work. We can look back at that for a second. So when we scroll up to the beginning of this method, here it is. It will do something to the frame hashing that is passed here. For example, it sets the eval pt scaled, which basically only initializes the frame hashing data. And then it traces a new course version of the frame hashing, and then does a bunch of optimization related stuff. Like, for example, adding the residuals here, new residuals for all points, then activate the points, optimize them, and then the function is finished. Okay, after that we will have a new method which is called makeNonKeyFrame. So this will be a void. It will be part in the full system, and it's called makeNonKeyFrame. This one will also take in the shared pointer of the frame hashing, which is a reference to the frame hashing. So here we will start with a block that first locks our pose mutex. So we create a unique lock. Of type mutex. And we call it CR_lock. And we pass the shell pose mutex. Just trying to figure out what happened to the music. Okay, now we can continue. I'm sorry about that. My Firefox had an update, so I had to restart it. Okay, so we have this unique lock here called CR_lock. And then we can take the frame hashing, and from that call the function or the method setEval pt scaled again, as before with making a keyframe. And we pass on the pose and the affine light parameters. So we take the frame hashing, from that we take the frame, and from that we call getPose. That's the first parameter. And the second one is we take the frame hashing again and the frame again, and then we get the f_g2l attribute. So this is what we do for preparation of this new kind of non-keyframe frame hashing. We need to prepare the data, and then after we have done that, we trace new course So tracing is basically, as far as I understand it, it is creating the imager points for a new image. So we take in the image, then we find new points in that image, and then those are imager points, and then they get active points at some point, and then we can optimize them. After this has been done, we take the frame hashing again, and then the frame, and say release all. Because here we no longer need it. It's actually written no longer needs it. Which is probably related to the... yeah, I don't know, to be honest. What is released here? We will be able to look at that once we have implemented the frame header file or the frame object. And then we will see what this release all method is doing. But this is probably also added to this make keyframe method here. Okay, here it is not added, it seems. So this is something, it seems, specific to the make non-keyframe method. But that's actually it. So this is the whole make non-keyframe method compared to the make keyframe method from here. This one is very simple. Still, what happens behind the scenes with this trace new course is a little bit more complicated. But this will be implemented in, I think, in a few lines of code in this file, in this full system. Okay, after that, we have a new method which is also assigned to the full system, of course. And then we call it marginalize frame. So here we marginalize a frame and then takes in a shared pointer of type frame, and we pass in the reference to the frame. Okay, so here we simply pass the frame hashing to be specific, to the energy functional. So we have the EF, the energy functional. Then we have a method, or we will have a method called marginalize frame, which takes in the current frame. And from that frame we can get the frame hashing. And this is then marginalized. So let's add a comment. Here we marginalize or remove all this frame's points. So the marginalization is happening once we are at a point in time where we have our sliding window that is being moved across our image sequence. And once we reach the end of the sliding window, we marginalize the frames, we marginalize the points, and this is what this marginalized frame is being, when this marginalized frame is being called. And this, we could say, simply removes all the frames points from the optimization. Next we drop all observations of existing points in that frame. That means we need to loop through all the frames and then through all the free features. And okay, I think that's a bot in the chat. Let me quickly Okay. Yeah, as I said, we need to loop through all our frames. So we make a for loop that just loops over all the frames. So we have a shared pointer here of type frame. And we call the iterator simply fr for frame. And we loop through all the frames that we have. Hey, how are you doing? Hi, Questa. I'm doing fine, thank you. How are you? Thanks for joining and welcome to the stream. Okay, so here we have our first loop, where we will loop through all the frames that we have. And in this loop we check if the current frame, the fr, is equal to the frame that was passed to this method. And if this is the case, then we will continue. So in essence, we will not continue with the rest of this iteration, but we will simply skip the rest here. I'm doing good, thanks. Ah, nice. Great to hear. What are you up to at the moment? What are you doing besides watching the stream, of course? Next, we have another for loop that now takes this current frame and loops through all of the features that we have. So here we create this time an auto data type. We call it feed, and we loop through the fr features. The stream comes in handy to watch in right now during my train ride. Oh, interesting. You're on the train at the moment. Interesting way to use the time you have. And hopefully there will also be something interesting. I'm just traveling back home. Okay, good. Then have a safe ride and enjoy the stream, of course. Okay, we have this auto feed that we are using from the current frame, and then from this frame we get the features, loop through every feature point, which is called feed. And here we check for the status of the feature. So if feed status, and we do not have this feature class implemented yet, so there are different attributes and fields in this object, in this features object, and one of them is the status. And the status is interesting because it is somewhat, I would say, it's somewhat related to a state or a how to call it, like a class of this feature. So let's make it concrete with an example. So we check if the status is from the feature object, then we will have a feature status there. And here we have, for example, a valid class or attribute. So this feature point that we are currently iterating over needs to have this feature status valid. And it will also need to have, once again, feed, then point status. So we will also have a similar state for the points of a feature. And for the point, the status has to be, here in this case, point from the point class. Then we will also have a point status here, similar to the feature. And the point needs to be active in this case. So let's add a comment. If feature is valid and point is active, then we do the following. We say feed and then point status. Oh, that's wrong, sorry. We first create a new point Hessian. So we have a shared pointer of type point Hessian. We call it ph. And we set it to the feature. Then we get to the point. And from that we take mpph, where ph seems to stand for point Hessian. I'm not sure what MP stands for at the moment, but we will find out. If you don't mind telling, what are you doing for a living, or are you still in uni? Yeah, I don't mind telling that. I'm a PhD student at a department that is working on autonomous driving. So I'm using this kind of to learn how the LDSO is implemented. So I'm doing my PhD at the moment. This is what I'm doing for a living. And currently, yeah, I'm trying to use the time wisely. Okay, this will be a shared pointer here, of course. Point Hessian, ph, like this. Next, we remove the residuals, project it into this frame. And for this we need to first get the number of residuals. Oh damn, that's cool. Thanks. Yeah, I like it. I like it. So we need to store the size type, basically an integer or something, which is called n, which is equal to the point Hessian, and then residuals dot size. Like this, so we get the size, and we can now use the size to iterate over our residuals. And then, as the comment already tells, we need to remove them. So let's make a for loop with a size t, which is prepared for us, ideally. And we have I equals 0, I is less than, in this case, the count is n. And then we increment I. Okay, and next we are now getting our residual. The data type is simply auto. Then we say r is equal to ph, and then residuals at position I. So we are looping over the residuals data type, which is storing all the individual residuals. And now we have one residual here. So let's maybe comment that. Residual for yeah, let's keep it residual. I don't know a better name at the moment. Okay. Now that we have the residual, we can check for r, then target.log. So this will be another method that will be provided from the residual object, which I do not know at the moment what kind of type this is. But we will have, yeah, a residuals type, definitely, as far as I can see later. So this type will have a target that we can log, and we can check that with the frame.frame Hessian. Or it will not be a dot, but a pointer. So the frame is a pointer, a shared pointer to be specific here. And each frame will have a frame Hessian. And this r_target.log will return a frame Hessian, it seems. Interesting. Okay, so if this is the case, so if the target log and the frame Hessian they are equal to each other, then we do another check. we take the point Hessian, and from the point Hessian we take the last residuals at position 0 and then dot first. So we take the first element of the last residuals list, and from that we take the first, which will then probably return the same type that we have in this auto here. That's why we can simply compare the to R. And if this is the case, then we say point Hessian last residuals at index 0 dot first is equal to null pointer. So we initialize it with the null pointer if they are equal, and else if the point Hessian last residuals at the second position, so at position index is equal to 1 dot first again, if this is equal to R, then we say point Hessian last residuals at the second position dot first is equal to null pointer. I have a mistake here. So this should also be a simple equal sign. And after we have done that, we say energy functional drop residual. And which one? R. And next we iterate through I. So we have this index here. And once we have removed this residual from the point Hessian and from the energy functional, we can say I minus minus. We simply decrement that. And we do the same to the N index, which is our index for the here for the number of residuals. So this is the total number of residuals, and this one, the I, is the current residual, or the current ID, the current residual ID, maybe something like that. Okay, then we close up all the curly braces here up until this point. We have the for loop. And next we want to, after we have removed the residuals from the points, we now want to remove this frame from recorded frames. And this is done by calling frame release all, which separately means release all things in this frame. So this release all seems to be somewhat a method that is just cleaning up stuff. Next we delete out order. Or create a delete out order. I have to think about that. So we create a new object, which is called delete out order. Let me finish writing it. Maybe it will get clearer then. So delete out order will take in a data type. The data type is a shared pointer to a frame. And it will be called using two arguments. For one, the frames, and for second, the frame. Okay, so as far as I can see it, this function is implemented probably later, and it's supposed to delete an element from a vector and keep its order. So we simply delete the frame, it seems, from the frames, but we will keep the order that the frames are sorted, how the frames are sorted currently. Okay, next we reset the optimization index, IDX. We do that using a for loop, where we loop through the unsigned integer I, which is equal to 0, and we say I is less than frames.size, and then we increment I, and in this loop we say frames at position I, index I, and from this current frame that we have, we take the frame Hessian, and from that we take the index and we set it to I. So we update the index of this current frame here. We need to do that. It seems to me we need to do that because we are deleting a frame from this frames object, and we still want the indices to be of ascending order in this case. So we need to update all the indices for all frames, and we do that in this reset the optimization index loop here. After that we call precalc, or no, we call set precalc values, which is probably related to the current frame that we are marginalizing. So we are in the marginalized frame method. So we set the initial values, and then we say energy functional, and then set adjoints F, which probably stands for frame, and we pass the hcalib object, which stores our calibration that we should already have, and from that we take the mpch, where ch stands for calib Hessian, I think. Okay, that's it for the marginalize frame method. But we also need to flag frames for marginalization. So this full system will also have this method called flag frames for marginalization. I hope I will not create too many typos, which I will then later need to fix, of course. So yeah, let's hope for the best. Shared pointer, frame Hessian. So this method will take in a new frame Hessian. That's why we call the reference new FH. And here we first check if we have, so if we have setting min frame h is greater than the setting of max frames. I think the setting max frames is related to the sliding window. So in the sliding window we have a total number of frames that we can process or store. And we are simply checking if this is exceeded in this case. So if this is greater. Okay, here we will loop through all the frames. We do that by creating a size t type data type object, call the index I and set it to setting max frames. And then we look for I is less than frames.size. And then we increment I. Here we will create a new shared pointer of type frame hashing. And initialize the fh, so the frame hashing, to frames at position I minus setting max frames. And from that frame that we have now, based on this index that we have calculated, we take the frame hashing. Once we have done that, we will log to the console an info message which tells us that frame, then fh frame kfid, which is probably keyframe ID, is set as marched. And then we end the line. Just I think standard end line to be more verbose here. And then we say frame hashing. We have for each frame hashing we have an attribute called flagged for marginalization, and this one is set to true. After that for loop has finished, we can return. So in essence, we have a specific max frame setting, which is again, I think, related to the sliding window. And if the frame age is exceeded, we simply go through all the frames and mark them or flag them as ready for marginalization. Let's say loop through outside of window, maybe. I think you're missing an R in marginalization in the signature. Yes, that could be true. Let me check where you see that in the signature. Yes. Very good. Thank you for helping me. That's nice. You're totally right. Flag frames for marginalization. Shared pointer. Yes. This will be funny once we are actually using the full system, and I'm saying funny because I lack the proper word here, but yeah, it will be a fight, I think, to get it to run. Yeah, 722. Just what is 722? Ah, 722, 722. Ah, yeah, okay. I missed that, yeah, okay. But I corrected it, I think. Thanks. No problem, just mention me in your thesis. Okay. Yeah. I don't think that this code will this code will go into my thesis, to be honest. But you are of help, of course. Thank you. Okay. Int flagged is equal to 0. So once we are finished with flagging all the frames that are outside the window, we then keep track of how many frames we have flagged. In the beginning it's 0. Okay, I'm sorry. Marginalize all frames that have not enough points. Okay, so here we marginalize all the frames that have not enough points. That means we need to loop through all the frames. So we start with the integer I is equal to 0. I is less than frames.size. And this will probably be some size t type, so we need to cast that to an integer, which is maybe weird because we could use a size t here, I think. But as I mentioned already, I do not want to touch this original code base too much. Merely just adding some comments, but that's it, basically. And some typos, as Questa noticed. So I will also add some typos here and there, probably. And this is my contribution to the code. And of course, Questa, yours as well, because you are fixing the typos. So yeah, it's a let's say a work we do together, like a cooperation or something. Okay, here we have a shared pointer. So we need to get the current frame hashing from the current frame that we have. So we create a shared pointer of type frame hashing, which will again be the fh object. Right, I gotta go now. Good luck with your work. Thank you. And thanks for helping, and yeah, have a nice day or evening. I don't know what time it is over there. But yeah, enjoy your day. Frames at position I. Here we take the frame hashing. So we store from the frames at position I, we store the frame hashing into this object here. And we will create an integer called in is equal to 0 and out is equal to 0. Same time zone. Oh, nice. That's good to hear. So it's not dark at the moment here, so maybe you can enjoy the weather a little bit if it's not too rainy. Okay, so here we have another for loop that loops through auto and feeds in frames at position I and then we get the features. So from the features we get one feature which we can use now. We say if the feed status is equal to feature status and then immature, we say, in this case, if the feature is immature, then we increment the in variable, in plus plus, and we skip the rest, so continue. And if this is not the case, so if we are not skipping, we create a new shared pointer of type point. We call it p is equal to feed and then point. And here we check if p and p status is equal to point status active. So this check is a bit yeah, not quite verbose here, so I don't know what this means. So probably this check is something like if p is equal to or probably not equal to null or something like that. Not sure what this means. If we simply check p. But if the point is active, then we will let me think. Okay, if this is true, then we will increment the in variable, and else we will increment the out variable. Simple as that. And this is it for this for loop, where we loop through all the features that we have in our current frame at position I, but we are still working with the current frame at index I. So after this for loop, we will now create a vec2, which is called ref2fh. So we have a reference frame and a current frame. So this is probably this kind of notion that we have a relative transformation, but we are not using the transformations here, but we are getting the exposure. So basically we say that this value is equal to f light. So the affine light parameters a and b. And here we call from to vec exposure. And this takes in the frames.back object, so the last object. And from that we take the frame Hessian. From that we take the AB exposure. This is the first parameter. And the next parameter, let me turn on the line break. View word wrap. So we take the frame Hessian, from that we take the AB exposure. Then we do the same with the current frame Hessian. So frame Hessian, from that we take the AB exposure as well. We also take again frames.back. From that frame Hessian. And here we take the FG2L. And we do the same once again with the current frame. So FH and then simply AF, AFF, G2L. So what this means is probably we take the value from the last element in our frames list. We take this AB exposure and move it to our current frame. So we do that with the AB exposure values, and we do the same with the affine G2L parameters. And this will be stored in a 2D vector, which means probably that ref to FH at position 0 is equal to AB exposure, and ref to FH at position 1 is equal to FG2L. Something like that, I would say. Let's call it result and move it below that. Okay, next we have some kind of marginalization conditions. If now we check our in and out variables. So if in is less than setting min points remaining times in plus out, or FABS, so floating point absolute value of log f, so floating point value of the logarithm of cast to float, the ref to FH at position 0 is greater than setting max log f fac in window. So this is the first condition and this is the second one. But we have a third one, which is linked with an AND operator. Here we cast to int. We take the frames.size minus flagged. So if the total frames, the total number of frames minus the flagged frames is greater than the setting for min frames, then we start with the actual logic. We have the log of type info. So we log to the console and we say frame, then fh frame kfid is set as marched. Then we end the line like this. We also need to flag the current frame hessian, so fh, and we say flagged for marginalization is equal to true. So we flag it and we increment the flagged variable. And this is it for this for loop, where we loop through all the frames. But in this case, we still have too much. Still too much. Marginalize 1. I don't know what we have still too much. Maybe too many frames. Which would be too much. Too many frames in this case. It could be too much. Too much. Too much. Yeah, we will see maybe. Let's continue with writing that. Let's not get busy with thinking at this point. Not yet. If int frames.size minus flagged. This is greater or equal to setting max frames. Then we create a double called smallest score, which is equal to 1. And we create shared pointers to frames. So shared pointer to a frame, which is called, the first one is called to marginalize, which is equal to the null pointer. And next we have another shared pointer of type frame, which is called latest. And this is equal to frames.back. For auto, now we loop through all the frames. So auto fr in frames. And here we are now checking for the IDs of the frame. So if frame hashion, and then frame ID. If this is greater than latest, frame hashion, frame ID, minus setting min frame age. So what this means is we are checking if our current frame ID is greater than the one from the latest minus the setting for the minimum frame age. So we are basically checking for a minimum age, I would say, here of the frame. The current frame. But that's not everything. So we have an OR with another condition, which is fr frame hashion frame ID is equal to 0. Or first frame, I would say. So if this is true, In this case, we say the current frame, then the frame Hessian, and then the frame. Oh, I'm sorry about that. That's the one above here. We simply continue in this case. Okay, if this is true, then we continue. And if not, then we create a new dist score, which we initialize to 0. And we then loop through all the pre-calculated values, which is interesting because this is of type frame precalc, and therefore the name is FFH. And we loop through all the frame. Let me remove that. FR, so the current frame, and from that frame we take the frame Hessian again, and from that we take the target precalc. So this is a somewhat pre-calculated value that we will loop through. That will help us to determine this distance score. So here we check if ffh.target.log and from that we take the frame ID. So it seems that this ffh.target.log, as before, gives us a frame Hessian, and from a frame Hessian we can get the frame ID, as we did here in this case. And we can check this ID to be greater than the latest frame. From the latest frame we take the frame Hessian and then the frame ID. This is what we need to do to compare the same, to compare apples to apples and not apples to bananas or something. And we subtract the setting min frame h plus 1. This is the first condition. So similar to before, we check again for a minimum h of, in this case, not the current frame, but, well, basically it is the current frame, but here we check for the FFH target log. Which is very confusing. But that's how it is, right? So here we have this min frame h plus 1, or we check ffh.target.log again. If this is equal to ffh.host.log, that's a function call. And if this is the case, then we will continue. So here we do two things. Check for minimum h of current frame, or if target is equal to host. So here's the concept of a target and a host, and I think this is related to the frames. So in the LDSO and the DSO, there are target frames and host frames. And what this basically means is that we have two neighboring images. So we have a left image and a right image, or a previous image and a next image. And this can be, these ones can be the target and the host images. So what we are doing here is we basically are skipping specific frame precalcs here. Okay. So if we do not continue, then we will create or calculate the dist score. This score is equal to, or it is plus equal to 1 over 1 e negative 5 plus ffh.distance ll. Okay, this is very cryptic. The first question is why this small value, which is probably some kind of epsilon, so like a very small, close to 0 number. And then we have some distance, but a distance LL. I don't know what LL means. So we will find out once we have implemented the frame precalc object. Okay, after this for loop, we then take the dist score again and multiply it with itself and the negative square root f, so the floating variant of that, floating point variant, fr. So we take the current frame. From that we take the frame Hessian again, and from that we take the target precalc dot back. So this is obviously some kind of standard vector, it seems, and from that we take the distance LL. So this FFH is frame precalc, and this target precalc dot back will also give us a frame precalc object, it seems. And both of them, or this object has the field distance LL. So this is being multiplied with the current dist score. After we have done that, we can check if the dist score is less than the smallest score and if this is the case, so if this is less than the smallest score, then we update the smallest score with this score. A simple check for the smallest value. And in this case we also need to update the to marginalize frame with the current frame, the FR. I will add this comment here, update frame that needs to be marginalized, and here we update the smallest score. Okay, next, after we have finished this, after we have finished this for loop where we looped through all the frames, we can now check if to marginalize is true, it seems. Then we do the following, we say to marginalize so to marginalize is a frame, it seems. Yes, of course, it's a frame. So from that frame we take the frame Hessian. From the frame Hessian we take the field flagged for marginalization. and set it to true. Then we also want to log an info to the console. We say frame, and then to marginalize KFID is set as marched, without an exclamation mark and without a full stop as well. And we end the line. And we also want to increment the number of flagged frames, so flagged plus plus. And I think this is everything for this method that is called flag frames for marginalization. Next we will have a big one, which is the optimize method. So this will return a float value, and it's called FullSystem optimize. And we pass the number of optimization iterations. So this is called, and this is an integer, and called mnum opt its. Yeah, this will do some kind of optimization, and this is of course interesting because the LDSO and modern Visual SLAM systems, they are all about optimization, optimizing error terms, energy functions. This is the core of every Visual SLAM implementation nowadays. But it is interesting that the LDSO and the predecessor, the DSO, they are optimizing, or they have written their own optimization function. So they are not using libraries such as G2O and Ceres and GTSAM and others, but they are actually, I think, implementing their own Levenberg-Marquardt solver. But we will see that maybe in this method here. So without further ado, we check if the frames.size, which is a field of the full system, so the full system has its own frames object, and this size can be less than 2. And if this is the case, then we will return 0. Because with 2 frames, or with less than 2 frames, so with only 1 frame, we cannot basically optimize anything. So we need a minimum of 2 frames. And this will be checked next. So if frames.size is less than 3, then we do at least update the mnum of opt its to 20. So we do not care about what is passed to this method here. We simply override it with 20. And if the frames.size is less than 4, so if we have 3 frames at least, then we can update the mnum opt its to 15 at least. Okay, so this is some preparational work that we have done here, and now we want to get the actual data that we are using for optimization, which is of course the residual, which is I would say the most important information for us. So what is the current error? And we also need to get some statistics about that. So let's write get statistics and active residuals. So we only want to use the active residuals, not like all residuals. And therefore we need to clear the active residuals list. So we clear that. And we create two variables for num points, which is equal to 0 in the beginning, and an integer for num L res, which is also equal to 0. Then we have a for loop where we create a shared pointer of type frame. We call it fr, and we loop through all the frames. So these are the frames that are, that one is a field in the full system, so the full system has a notion or a memory of all the frames. This might be relevant later. Then we have another for loop for auto. And now we loop through the features. So we have a reference to the feature. And we get that by calling the frame. And from the frame we get the features. Okay, so we are now iterating over all the frames, and for every frame we iterate through over the features. So we need to store the specific point of such a feature now. So create a shared pointer of type point called p, which is equal to feat point. And here we check the status of the current feature. So we say if feat status is equal to feature status valid and p. So if p is true, or if it has some kind of value, so if the point is set. And we also check p status is equal to point status, and then active. So this needs to be an active point. Check for valid feature and active point. Maybe let's add here set plus active point. And here we create a new variable, auto ph is equal to p. And then we take from the point, we take mp ph. So this is basically the point hashing, I would say, even though it's the auto data type here. And for the for loop, we now loop through all the residuals that we have in the point hashing. So we once again write auto. We say we have this reference to the residual, which is in the list of ph, the point hashing, and then residuals. Here we check if not the residual is linearized, in which case we say active residuals dot push back the current residual. So if the residual is not linearized at the moment, we put it into the list of our active residuals. And we also say r reset OOB. And this OOB, I think, means out of bounds. OOB out of bounds. I think, I'm not sure, but I think this is what it means, because If you imagine you have an image, so basically one frame of your video sequence, then the points may be occluded or outside of this image, which would mean out of bounds, as far as my understanding tells me that. In the other case, we want to increment the num_l res variable. And after we have finished this this check here for the feature status and the point status, we want to increment the number of points. Because here in this loop we are looping over all the features, or I'm using it interchangeably now, features and points, but basically a feature consists of a point in this case, as you can see here. So at this point we have incremented the number of residuals. So what this L means I'm not sure, but this is the number of residuals and this is the number of points, which we wanted to know here. So now we have finished this loop and can continue with an info to the user. So we say log info active residuals and then active residuals dot size. If I can type, of course, and then std end line. So here we will print the number of active residuals that we have, and now we want to do something with them. So we create a vec3 called last energy, and we initialize it with the function call to linearize all with the parameter false. Then we have a double last energy L, which is equal to calc L energy, and we have another double last energy M, which is equal to calc M energy. Okay, after that, we have initialized the last energy and the last energy L and M. Not sure what L and M means here in this case, but we will find out, I think, in not a long time. So first we want to apply the res, which is probably standing for residual. Not sure, let's see. So we check if multi-threading is true in this case. Then we want to continue with the music first, and then continue with the thread reduce dot reduce. So we need to do something specific to multi-threading here. And we have a separate thread which offers us a reduce method, and we pass on the bind result to that by providing a reference to that bind to this bind method, a reference to the full system. And here specifically the apply res underscore reductor, which is, I think, a function that needs to be implemented. Oh, I think we already have that. So 878. No, we do not have that yet. Okay. So this needs to be created at some point. But this will probably be a function. And we pass on this true _1, _2, and _3, and _4. So this apply res reductor method will have 4 arguments. And this is basically, I think, from the boost library, a method that will provide this function pointer. Okay, I'm wrong. This bind is from the standard library. But I think there's also a similar method in the boost library. Next we pass 0 and active residuals dot size. And we also pass 50. Let me quickly copy that from the original code base so that this will make a little bit more sense. So this reduce method here, it is implemented in the LDSO internal index thread reduce later. So we do not have this yet, but this is implemented here. It will take in a function which takes 4 arguments, as I already told here. It will also take in here the first integer and the end integer and a step size. So to make it a little bit more readable, we say that it means first is in our case 0, end is active residuals dot size, and the step size is 50. These are very specific parameters which do not make sense at the moment, as we do not have this apply res reductor function. But maybe it's interesting to know that we are passing this kind of value. So we have first, an end, and a step size here. Okay, if we do not have multi-threading, so else, we say apply res reductor, written in the same way as above, so the same way as here. We simply call the function directly. So we do not move it onto a different thread, it seems, as thread reduce, but we simply call it, and this will probably take some time and block the thread. Okay, apply res reductor, and here we have similar parameters. So we have true, we have 0, active residuals dot size, 0 and 0 this time. So the step size is 0 here, it seems. I'm a little bit confused about the number of parameters, because here we only have 3 and here we have 4 parameters. This confuses me a bit, to be honest. But unless we do not have this apply res reductor implemented, yeah, I can only speculate what this means. And I will not do that, so let's continue. We will print optimization res, where I think res means result in this case and not residual. But this will be a function call that we need to implement later. And we pass the last energy L, last energy M, 0, 0, and frames.back. From frames back we take the frame hashing, and from that we take f g to l, which is a function call, and then we take dot a, and we do the same with the b parameter. So here we directly pass the a and b affine light parameters. So the print method here will need this individual values here and not just the affine light object. Okay, let's create the semicolon here and continue with double lambda. Lambda is equal to 1 e negative 1. Then we have a float step size, which is equal to 1. And then we have a vec x called previous x, which is equal to vec x. From that object we create a constant vector, which we initialize using cparse plus 8 times frames dot size and none, so not a number. So we initialize a vector of size cparse plus 8 plus times frame size. So for every frame we have 8 parameters, and it seems we also are adding the camera parameters here, and we are all initializing the total number with not a number values. Then we create a for loop with int iteration, which starts at 0, and we check iteration is less than the argument that was passed, like m num opt its, and then we increment iteration plus plus. Okay, here we now want to solve. First we back up the state with the iteration not equal to 0. So we check if we are not at iteration 0, then we want to back up the state, and then we solve the system. We pass the iteration and lambda. Okay, but now we do some interesting linear algebra here. So we want to save a double first with increment dir change, which is probably the incrementation direction change. And this one is equal to 1e to the negative 20, so a very small number, plus previous x dot, and we pass the energy functional last x and this is divided by 1e negative 20 plus previous x dot norm, and then multiplied with ef last x dot norm. So we are avoiding that this norm or this one is 0. That's why we add this very small number. And this way we avoid the division by 0. And then we are multiplying the previous x with the last x. So this is being done first, and then we divide by the length of those vectors. And we get the change in direction, which is a simple double, because this is only like the magnitude, I would say. It's not really a direction, like an arrow or like a vector, but it's just a magnitude we calculate here. And next we say previous, precious is also nice, previous x is equal to ef dot, or in this case it's a pointer, last x. Then we check if standard is finite. Inc dir change, that value that we have calculated before. And setting solver mode and solver step momentum. Okay, so we check for this value to be finite, and we want to set the solver mode to step momentum, it seems. Let's add a comment. Magnitude and so we are preparing the solver at this point. You want to create a new step size and set it to exponential function of inc dir change times 1.4, and we check if inc dir change is less than 0 and the step size is greater than 1, in which case the step size should be set to 1. Else we set the step size okay, not else, but we do it anyway, so we update the step size next with the square root as a float version of the square root of a new step size. So this is the one that we have defined previously, This one here, the exponential of this ink direction change. So this new step size times the step size that we have defined probably above here, like here, this step size of 1. Step size, here step size times step size times step size. So we are updating the step size, and then we need to check if the step size is greater than 2. If this is the case, then we change the step size to be exactly 2. And if the step size is something negative or close to negative, less than 0.25, then we set the step size to 0.25. So here we are check the bounds of step size to be in 0.25 to 2.0. Okay, then we store a bool called canBreak, which is equal to do step from backup, and we pass in the step size 4 times. No, 5 times, sorry. So we have this 5 times. And this will give us a bool that tells us if we can break. So if we, I think, can break out of this loop for the iteration. So here we are going through the optimization through each iteration, and we check if we can break here, if we can break out of this loop. But first we want to eval new energy. That's why we do the same as before with this last energy. Copy that and put it here. And we do not call that last energy, but this time new energy. New energy L, and new energy M. The rest is the same. And we can print opt_res with this time, let's copy that as well, just as before. This time we want to print the new energy L, and the new energy M of 0, 0, frames back, frame hashen, affine G to LA, and the same with frame hashen affine G to LB. And now we want to control the lambda in LM, where LM I think stands for Levenberg, not Levenbergy, Marquardt, which is some kind of nonlinear optimization solver. And to do that, we need to check if setting force accept step or new energy at position 0 plus new energy at position 1 plus new energy L plus new energy M. If this sum is less than last energy at position 0 plus last energy at position 1 plus last energy L plus last energy M. Then we want to do something. First we want to realize that the energy is decreasing because this one is last. This is less than the last energy, the new energy. So we are actually improving something, it seems. So we need now to check if we have multi-threading. In this case, we call thread reduce dot reduce and then bind. Take the reference. Maybe let me copy that because it's quite a long, complicated line here. It's not complicated, but it's a little bit of work to write that. So we call thread reduce dot reduce and then bind the full system, apply res reductor. We pass this true and we have the placeholders for the 4 arguments and we pass 0, then active residuals dot size and 50. Else we do basically the same, but without this use of the thread, which means that we are simply calling apply res reductor with the parameter true. And 0 active residual size 0, 0, like this. Okay. After this check has been done for the multi-threading, we update the last energy to be the new energy and the last energy L to be the new energy L and the last energy M to be the new energy M, like this. And we also update the lambda by multiplying it with 0.25. So we are taking 1/4 of the previous lambda value and hopefully converging. When I say hopefully, that means that there's not only the possibility that we can decrease that the energy is decreasing, but we also have a condition or a case, not else if, with the energy increases, reload the backup state and increase lambda. Here we load the state backup, which is, as I mentioned in the previous part, probably a typo. Should be called load state backup, but I can work with that. And we update the last energy to be linearize all of the parameter false, and last energy L to be calc energy, which is a function call. We have last energy M as well. So we have calc L energy and calc M energy. Like this, and we update the lambda times 1e2, it should equal 100, I think. So 10 times 10. Let's make it more verbose. Lambda okay, that was probably not necessary, but I think it might help at some point to understand that. So the main difference is that the lambda values are decreased here, and here they are increased if the energy increases or decreases. Okay, after this check for the way how the energy is behaving, we want to check if can break and iteration is greater or equal to setting min opt iterations. So if we have reached the number of total iterations, or if we have found out that we can break, then we break. Simple as that. And this will finish the for loop where we iterate through the residuals, I would say. Well, not really the residuals, but yeah, through our solver. We solve the system for every iteration. And what is happening here is the actual magic, I think. And the confusing part is that this solve system will change variables of the full system, which allows us to create some unwanted side effects, I would say. So I have to say that I'm not really happy with this way how it's working, but I'm also not happy with the way that I have written this line of code here without a semicolon. Okay. But once we have found out every energy change and the lambda values, we can say we can break, maybe, hopefully. And if not, we continue with the iteration and continue with the optimization of our values. Okay, once this iteration is finished, we now need to evaluate what happened. So we create a new vec10, which is called the new state 0. As the name suggests, we initialize it with vec10 0. So we create 10 zeros, put it in this 10D vector, and we now need to fill that. So we say new state 0 dot segment of length 2, I think, at position 6. Oh no, it's probably length 6 at position 2. So the third value plus 6 values in this vector. We initialize that to frames.back, and then we take the frame Hessian, and we get the state dot segment at position 2, the 6 values. So we basically update the new state 0 vector with the current state of our last frame in our frames list. From that we take the frame Hessian, the state, and take the 6D vector from position 2 until position 2 plus 6. So we just update the contents of this 10D vector. This is interesting because this will hold all of our interesting properties of our state, which is probably the camera position and translation, but I have to say that I'm not sure about that. Okay, here we want to also get the back of the frames list and the frame Hessian from that. And then we want to call set eval pt and pass frames.back, and here the frame Hessian, and then the pre world to cam, and then the new state 0. So this is the transformation from the world to the camera, the previous, it seems. And we use it together with the new state 0 to basically check or update as well our data. I think this function will also be very important, as this is probably doing the projection, the reprojection from the host frame to the target frame. But I'm not sure at the moment, so we need to continue. Next we have ef delta valid is equal to false, and ef adjoints valid is equal to false as well. And then we have the energy functional set adjoints f for the frame. We pass the h calip, mpch, and set precalc values. Like this. And we get the last energy. This is equal to linearize all, and we pass through here, which means fix all the linearizations. And then we check if not standard is finite, cast to double, the last energy at position 0, or similarly last energy at position 1, if this is not finite, or again not is finite, last energy at position 3. Yeah, 3 or index 2. So 0, 1 and 2. So if this energy, the 3 energies, maybe let's put it like this. If these 3 energies are not finite, then we log a warning to the user, telling him or her that the KF tracking failed. And here we are lost. Which is very bad, because as far as I know it, the LDSO cannot recover from a lost tracking. Of course, we also need to set the isLost value to true, so that we can check for it in other places of our system. Next, we want to set the estimated pose into frame. This will be done in a block. First, we need to get a unique lock. So basically a mutex. We call it CR lock and call that object, or pass the object shell pose mutex. So we have created this mutex already. And now we can, with this lock, we can now loop through all the frames. So we write auto fr in frames. So fr is one single frame from the frames list. And here we say fr set pose fr frame hessian pre cam to world dot inverse, like this. Next we check if fr kf id is greater or equal to global map, and then get latest optimized KFID as the latest optimized, so the latest optimized keyframe ID. If the current keyframe ID is greater or equal to the latest optimized keyframe ID, this is a function call. Then we say the frame set pose opti with sim3. This is from the Sophos library, similarity transform, and we pass the fr get pose dot matrix. So we take our current pose of the current frame, we extract the matrix, create a new sim3 matrix, and set the optimized pose using that of the current frame. Then we have the frame fg2l is equal to fr frame hessian fg2l semicolon. Next we want to return the square root. It has a floating point number, so we cast a float the last energy at position 0 divided by the pattern num times the energy functional And from that we take the res in A. Res in A. And that's it. And that's indeed it, because this is the whole optimize method finished at this here. With returning the square root of the last energy divided by the pattern number times the residual in A. Okay, next we have a method called setGamma_function. So full system setGamma_function. This one takes in the pointer to the binf image, which we have created from the photometric undistorter. Yeah, this can be the null pointer if we do not have it. So we need to check that. So if binf is equal to the null pointer, then we return from this method. Else we want to copy the binf . Where do we want to copy that? We want to do a mem copy. Between hcalib, mpch, and then binf, and binf. We need to pay attention to the I, to the capitalization of the I. Here it is written in small letters, and here it is written in capital letters. This might be something I would change later. And we need to pass the size, proper size of the buffer, which in this case is simply a byte. So 256 times the size of a float. Okay. After that we need to invert. That means we need to loop through all the individual photometric calibration values, and we can have 256 of them. So this is why we have this 256 here, not because we have a byte, but because we have so many individual float values. That's why we need to store that here. And we now loop over them. So int I equals 0, I is less than, in this case, 255, and I++. And here we do find the val such that binf at position val is equal to I. And there's another comment which is not from me, but it's from the original authors. So I don't care about speed for this, so do it the stupid way. Okay, what is the stupid way? We create a for loop where we start with the int s variable at the value 1, and we check for s is less than 255 and s is incremented, And after that we check if B inverse, and you need to pay attention to the capitalization, B_inf at position 0. Not at position 0, but at position S. If this is less or equal to I and B_inf at position S plus 1 is greater or equal to I, so if we are in the range, then we want to call hcalib mpch and then b at index I, which is equal to s plus I minus b_inf, and then at position S divided by b_inf at position S plus 1 minus b_inf at position S. So this is the update of the B value in our calib hashing ch. And after that we break that for loop, because we have found the value that we are looking for here. The last thing that we need to do is we need to update the limits of our hcalib. That means we have the hcalib object, which is a field of the full system. And here we have mp calib hashing and then b at position 0. This is equal to 0. And similarly with position 255, this is equal to 255. So we are avoid imprecise values. So the start of B should always be 0 and the end should always be 255. This needs to be ensured. I'm not sure why this is the case. But given the gamma curve in the paper of the DSO, this would make sense. Okay, next we have a shared pointer as a result from a new method, which will give us a point hashing. And the name of the method is FullSystem, and then optimize immature point. This one will take in a shared pointer to the internal namespace, and then immature point, which we do not have yet. We pass in a point and the integer of min ops, and a vector of type shared pointer, and then of type immature point temporary residual. And we take the reference to the residuals. Like this. And the body of this method starts with defining an integer for the number of residuals, which is 0. Then we create a shared pointer of type frame, which we call the host frame. And this will be initialized using the current point that was passed here. Then we get to the feature, and then we get to the host, which I think is a host frame. And then we take, then we lock that. Of course it's a frame because we have the shared pointer of type frame. And the name is also host frame. Next we assert if we have this host frame. So this will hopefully pass. And this means that the feature should have a host frame. Okay, so we need to extract the host frame. This is important. Once we have that, we loop through all the frames. So fr in frames. And then we check if fr is not equal to host frame. So where do we get fr from? Okay, it's iterating through frames. So we pay attention if the current frame that we are iterating through is not the host frame. If this is not the case, then we update our residuals. So we have this residuals list, residuals, that was passed to this function. And we say we want to get the residual at position n res, which is 0 in the beginning. And from that residual, we want to get the state new energy. We want to override that with residuals at position n res, and then state energy, and this is equal to 0. So we initialize it to 0. Then we have 3 more variables. We have the state underscore new state, which is equal to res state and then outlier. Then we have the state underscore state, which is equal to res state in. And then we have the residuals target, which is equal to fr and then frame hashing. Lastly, we need to increment the nres variable, because otherwise we would not move on. After the for loop, we want to assert that the nres number is equal to the frames.size -1. Because we are iterating over all the frames, so we are expecting that we are incrementing the number of residuals to the same size of the frame's size, -1. Because we start here at 0, that's why we need this -1. If we would start at 1, this would not be necessary, but this would also change this logic here, which is probably not good. Okay, here we are finished with the assert line, and we can now continue with a float that we define for the last energy, which is equal to 0. And we do the same for the last HDD, which is also 0, and the last BD, which is also 0. And then we have another float called current I depth, which is equal to point and then I depth max plus point I depth and then min, and the whole sum divided by 2, so times 0.5 f. Next we loop through with int I is equal to 0, I is less than nres, and I plus plus. We loop through the number of residuals, so we say last energy plus equals point, and for each point we are now calling linearize residual, and we pass the hcalib object. From that we take the mp calib hessian and then 1000 residuals at position I, and then last hdd, last bd, and current I depth, semicolon. So this is how we update the last energy. Now we need to update the residuals as well. So we have residuals at position I, and then state energy. No, state I mean. This is equal to residuals at index I, and then state new state. And similar, we have state underscore energy, which is equal to residuals at position I, state new energy. Oh, hi there. Welcome to the stream. Sir Dice a Lot 7. Ah, interesting name. How did you come up with that name? That's funny. Sir Dice a Lot. Okay, so next we check for the if not is finite, last energy, or last HDD is less than setting min I depth h act, which is very cryptic as well, once again. And if this is true, then we want to return 0. We are in the optimize imager point method. It's been so long that I do not remember. Okay, yeah. I have this. I also have this kind of cases where something is very long ago and I cannot remember. Okay, so after we have checked this last energy to be finite or not finite, and if the last HED that we have calculated, here in this case, to be less than the setting, if this is true, you want to return 0. So this optimized imager point will return 0, which is weird, to be honest, because we are expecting a point Hessian. So I think it would be cleaner to return a null pointer, and that's why I will add this here as a to-do for me. Better return null pointer, which should be the same because the null pointer is only like a macro for the 0, but yeah. I would expect the 0 to be a float or a double. Yeah. But I will not touch the logic at this point, as I mentioned multiple times. That's why I will continue now. Okay, after this check, we need to check if the new energy that was calculated is less than the last energy. So we are, let's add a comment. Check if the energy is decreasing. If this is the case, then we want to update the current I depth, which is the inverse depth, I think, to the new I depth. So we are actually improving here. We are improving during our optimization. That's why we need to update the values with last HDD the same. So last HDD is equal to new HDD and last BD is equal to new BD and last energy is equal to new energy. We do the same for the residuals. So for the residuals we need to loop through every residual. So we create a for loop with int I is equal to 0, I is less than nres and I++. And here we update the residuals. So residuals at this index I, then we take the state, which is equal to residuals at position I, and then state, new state. And the same as we did above, we do the same with state underscore energy, and then residuals at position I, state, new energy. After that we need to update our lambda. So lambda is lambda times 0.5. And if we are not increasing, if we are not decreasing, I mean, so else we set the lambda to lambda times 5. Okay, let's add this comment here for completeness. And after this check has been done, we want to add another check for the absolute value, FABS F of step. If this is less than 0.000, actually only 3 zeros, 1 times current I depth. I have been using AutoWare to help implement SLAM on a vehicle for a competition. Oh, that sounds interesting. What is AutoWare? I do not know that. I would appreciate it if you could maybe explain what this is. To help implement SLAM on a vehicle for a competition. And what competition was that? Was it like a big event, or was it yeah, what are you doing? Maybe you can go into more detail about that. And what was your experience? That's maybe the most interesting part in that. Okay, so if this is true, then we can break the loop. the loop where we oh, I may have made a mistake. Ah, okay. I have made a mistake. I have forgot something. Okay, let me quickly back up here. So we have the frame, which is called host frame. We get that. We loop through the frames. We update the residuals and the nres. Then we assert. Okay, so far it's fine. Then we have our energies computed. Then we loop through the number of residuals. We update that. Then we check for is infinite. Okay, and here is where I have confused myself, because here we want to do LM iteration for this imager point. This is what is missing. I completely skipped that, it seems. Okay. So we need, of course, the lambda first. Lambda. Float lambda is equal to 0.1. This is our initial value. Okay, let me read that. AutoWare is built on top of ROS, okay, the robot operating system. It consists of all the functionality required for autonomous driving, i.e. perception, planning, control, in a modular architecture, and has a good interface and fairly useful APIs. It allows you to just plug in into your algorithms and it handles the rest. Okay. Ah, it's similar to ADTF, I think. But it builds on top of ROS. Built on top of ROS. Okay. Oh, I didn't know that. I have to look it up later. Sounds good. Why is it not just using? Okay, it's built on top of ROS. Okay, I was a bit confused why it's not just using ROS, but if it's built on top of that, it's obviously using it. So yeah, it's fully open source as well. Oh yeah, nice. And what? Let me quickly check. So what did you? You implemented a SLAM. Okay, and what sensors did you use for the SLAM? Because there are many variants, right? There's like visual SLAM, laser SLAM, radio SLAM. And what kind of work did you have to do there? Because I mean, there is some software stack, it seems. Camera and LiDAR. Ah, okay, interesting. Camera and LiDAR, that's a nice connection. Do you have code online, maybe, where I can maybe look into what you have done and how it works? Because I mean, I can look it up, of course, but if you have your own project, feel free to post it, to link it. It might be something I can also look into for my projects. Okay, so here is this for loop that I'm missing. For int iteration is equal to 0. Then we have the iteration less than setting gn its on point activation, and then iteration plus plus. And here we need to add some lines of code. So we have a float h, which is equal to last HDD. Then we have h times equals 1 plus lambda. We could check this the chat. I can discuss my work, but I cannot put my code online, unfortunately. Mostly to avoid students finding it and cheating. Okay. Yeah. True. Yeah, that's maybe not a good idea. Unless, of course, you're posting like a template or something where they can start from. But you probably... So you're working at university, I suppose? Or at a private company where you have students, where you teach something? Sounds interesting. So you're teaching Slam? I'm a graduate research and teaching assistant. Okay. Nice. Where are you working, if I may ask? And in what country? So what university? And I'm teaching a class called Introduction to Autonomous Driving. Wow. Perfect. Maybe I can learn from you, because I'm currently trying to learn all the stuff here, and it's just complicated. The US is where I'm from. Okay, great. Then welcome to the stream, and nice to have you here. Are you maybe also interested in something specific? Like when you watch the stream, you probably, yeah, I don't know if you want to learn something, but maybe there's a reason for why you are watching the stream. I would be interested in knowing that. Okay, so here we are initializing the values for the optimization. So we also need to have a float for the step, which is equal to 1.0 over h times the last BD. Then we have a float new idepth, which is equal to current idepth minus step. The class assignments are mostly ROS and AutoWare, while localization, controls, perception, etc. are covered in lecture. The algorithms are provided, and they have to use ROS and AutoWare to put them together to get the car running. Wow, that's interesting. If they want more specifics, they can take a controls class, AI class, vision class, localization. Yeah. Okay. So you are fully equipped, it seems, with the theory and also practical examples, which is very nice. And are you using the LDSO in your class as well for the visual, like the Visual Slam? Or do you have implemented your own Visual Slam maybe? Which would make the whole discussion even more interesting, in my view. So I'm interested in how, like, are you like really, do you have a strong background, your university, your like institution, in every field, or do you like have expertise in specific area? Maybe we have a custom SLAM algorithm another graduate student made for some time ago. Oh, okay. Nice. And probably it's in C++ because you're using ROS. Well, ROS also works with Python, but for efficiency, I suppose you have it in C++. University main area is expertise in everything. Okay. Wow. It is probably a big one, I would say. Because like everything, automotive and mobility, it's a huge field, right? So I suppose, I don't know, is it really everything, or are you still like specializing a little bit at least? Obviously SLAM is one core component in your work, it seems. Float new HDD is equal to 0. Float new BD is equal to 0. And float new energy is equal to 0. And we have a for loop with int I is equal to 0. I is less than nres and I++. Here in this for loop we compute the energy in other frames. My specialization is neural network architecture design for perception. Oh, okay. Yeah. Very modern, of course, at the moment. But still... okay. Neural network architecture design. Yeah, I'm asking myself if I see those when I see those neural networks, I'm also asking myself, why are they choosing this number of layers and this number of input and well, okay, input and output neurons is maybe clear, but what is happening in between, right? What kind of activation function are you using? What kind of what kind of activation function and what else? Well, there are many parameters. I'm just curious how you go about like choosing the architecture. Is it simply trial and error? Or is there a concept like where you say, okay, this layer is responsible for, as you have with the, I don't know, the YOLO network or other convolutional networks, where you have this first part which is doing feature extraction, for example, and then you have those other layers and networks. Like, I'm interested in how do you... Is there really I'm sorry, I'm just searching for the correct words. Is there really like how is it called? Can you really describe a neural network completely, like the architecture, what is happening in all the layers, or is it still some kind of black box? That's what I'm trying to ask here. Okay, my focus is on making super lightweight ones. Okay, for what I am working on now is like, this layer is responsible for low-level feature extraction. Okay, these layers are responsible for decoding, etc. Okay, can I ask questions like, can we reduce the number of filters in this convolution layer? Okay, yeah. So you obviously have quite a good knowledge about what is happening there. So you're not simply guessing, it seems, like I would do, for example. But there is a clear concept behind that, and that's what we are looking for, right? And can you put your finger on that? Like what? Like this layer is responsible for decoding. Can you really control that when you do that design of this neural network, or is it still some kind of black box at least? Okay, more like an educated guess. Okay, yeah, I see. Okay. So, as far as I understand, we are not yet at this point where we can clearly describe such a neural network, but we are getting there, right? Yep, every design choice I make is very intentional. I even look at the neural structure of each layer. Okay, what do you mean by neural structure of each layer? Like the like the details, the activation function and the number of neurons, or what do you mean by neural structure with this term? New energy plus equals point linearize residual h calip mpch 1 residuals new hdd ubd new idepth. The topology of the layer. Okay, topology means the interconnection, right? Like what layer is connected to which neuron. For activation functions, I pick them based on the complexity of the task and the hardware available. Okay. Can you name an example of what tasks you are solving at the moment? I mean, I maybe do not want to go into detail. By the way, this this stream will be published on YouTube later, so if you like write something very specific or very personal, then others can read it. But maybe it's fine. Topology of the layer, the activation function, okay. Like if I am just performing binary segmentation in a static environment, really would work. Okay, the rectified linear unit would work fine. Binary segmentation. Okay, so the questions that I have when I read this, I'm like instantly asking myself, like, okay, why is the relo working fine here? I imagine this relu as like a nonlinear function, which has like some domain that is 0 and one that is a linear function. So those are like two areas. Is it like for the binary? Like, okay, I have this object segmented. I have this foreground separated from the background in my segmentation, and that's why the relu is working. It's probably not that simple, right? So this is what I'm like, what I would like to understand. But I'm not working in this neural network area, so I'll probably never understand, but we'll see. There are only two classes in the image at most. Okay, yeah. So it's like foreground and background, one could say. It's probably really important to boil down the problem to something really like, I do not want to say simple, but if you imagine you have an image and you have like cars, people, and I don't know, birds maybe, you have this complexity is really blowing up at some point, and to understand the networks, I think we really need to, as you say, make, how did you write that, super lightweight ones. So really, yeah, trying to keep that problem space limited, right? I don't know if you understand what I mean. I'm not a native speaker, so sorry if that's not very clear, maybe. Okay, I will now move this part into this for loop, because this is this should be here after this. like this. So I'm missing this. I'm missing this check. So I need to implement this here in this line. Okay, so this one, if. But I think I have written this somewhere, if, and then return 0. Ah, it's here. Oh, you're following me now? Oh, thank you very much for your follow. It's really hard for me to see that because I do not have those sound alerts on, and sometimes I'm missing it. So thank you. Okay, I need to insert this here. And let me quickly check if this is correct. If not, standard is finite, last energy, or last HED setting. Okay, return 0, yes. This is the same as above. And with this last check here, we can break out of this loop. And we can continue here with the is finite again. Okay, I think I will finish this method and then I will quit the stream because I'm running out of time. I still have an event today where I need to go. It's nice to meet another person interested in these topics. Oh yeah, yeah, I totally agree. It's always nice to talk about this stuff, because sometimes you are, well, at least it's for me like that I'm working on this stuff and I don't want to say that like the others are not interested or something, but just talking about it with maybe a complete, like, I say stranger, but with someone you do not know, it's often helpful to develop new how to say that, to develop a new view on the things, like what you just described here with the design of the neural networks. I was always asking myself, are there actual people that are understanding the neural networks? And now I met someone like you who is actually understanding them. So yes, it's very interesting, and it's you can learn from that a lot. That's why you go to conferences as well, right? So it's great to have you here. Thanks for joining the stream, and yeah, it's nice to have this discussion. There's not much of a need to understand these days with how good most of the shelf models are. Yeah, when they are working good, but when they are not, then you need to understand it. And I mean, there's a whole lot more to that than probably only, like, not only, but there's a lot to control here, in my view, because of course the architecture is one important thing, but then what about the data that you provide? They are not optimal for the every task, but usually good enough. Yeah, true. But you need to be able to select the correct pre-trained or created model. Like you, I don't know, if I, for example, look for some model to do image segmentation, then okay, I see this unit architecture, and then I ask myself, okay, I can use it, and it works for specific cases quite well. But for example, for my case, it did not work very well. Because I had a project where I had to segment watermelons in an image. And it worked for specific, like, for specific images, but for others it did not work. So in this case, I need to understand why it's not working, and for this you need to know a lot about what is happening in this neural network, right? Okay, yep, model, architecture, data quality, training parameters, yes, yeah, there's a lot. Yeah. But it's nice to know that we are getting there. So we are not like using these as black boxes, but there are people like you working on building a fundamental understanding on how those neural networks are behaving. Okay, I will continue with the program. I think there are 20 lines of code or something. So I will finish it. And then I will end the stream for today. So here we continue with the if not standard is finite, current depth, current eye depth. So we need to check the calculated eye depth value that is based on the new eye depth. So if this is not finite, then we want to return, and here it is, return null pointer. So here they are returning a null pointer, but here they are returning 0. And this is why I would change this return a null pointer here to replace this 0. But as I said, I will not touch the implementation due to reasons which will be apparent later once the full system is actually being used. So we are very interesting part of this live stream series. Here is an integer num good res is equal to 0. I'm glad I have a MATLAB license provided by the university. The libraries it has makes creating and modifying models so easy, and I can still just export it to a TensorFlow, save model once and done. Yes, I think you mean the toolboxes that can be bought with MATLAB, right? I mean, there's MATLAB and there are those toolboxes, and yes, I like them a lot as well. But I have to say that I'm not a big fan of MATLAB, of the like the programming language. Yeah. Otherwise, I would probably use it more often as well. We create a for loop with int I is equal to 0, I is less than nres, and I++. In each iteration, we check if the residuals at position I and then the state is equal to the res state in. If this is the case, then we want to increment the num good res value. And after this for loop, we check if num good res is less than min obs, which means we have an outlier. And therefore we return the null pointer. I know I can't rely on it forever, but it saves a lot of time. Yes, generally. I mean, also with what was the website called? I think Hugging Face. I think Hugging Face is the website that provides some nice demos online where you can try out specific models. Also some kind of ChatGPT variants I think have been there, and segmentation models and depth estimation models. Just being able to try out stuff that is already working obviously saves a lot of time, yeah. That's true. But I think I have bought a MATLAB license. We also have one at university. But I think it's also only available to students and not to employees. But I have to check. But it's not very expensive. I think it's only like, wasn't it $60 for a year or something, plus the toolboxes? I don't know. I have to look it up. But yeah. I have bought my MATLAB version, even though I would probably get it from university. An academic license is cheap, yeah. Yeah, true. Yeah, I have that here. But as I said, I'm not a big fan of this programming language, so to try out stuff that is already prepared, everything is fine, but yeah, working with the language is a different story for me. But of course, everything is simply a time investment to learn it. And ideally we learn the concepts which we can then apply to other situations, to other programming language and stuff. I worked for automotive companies in my internship, so I got used to MATLAB. Yes. Yeah. Working with that helps, of course. Yeah. Create a point from image feature. Shared pointer. Point hashing. P is equal to point feature point mp ph, which is probably the point hashing here and not the calip hashing as before. Then we set the residual status in a new map point, which means we have the p, the point hashing p, and we get the last residual at position 0 dot first is equal to null pointer, and the second is equal to res state OOB, so out of bounds probably, and the second index, first and second, is similar, res state OOB. Okay, so we initialize the last residuals, the first and the second one, and for each residual the first and second, with a basic first state. Then we say p set I depth 0 based on current I depth, and we also want to set the I depth without 0 with current I depth, and then we want to move the imager point residuals into the new map point. And this will be the last big for loop before we return from this method, which is called optimize imager point. So let's create this here. Create this for loop. Int I is equal to 0. I is less than n res I plus plus. If, by the way, I'm now noticing that doing this live stream also helps to get like, yeah, to get in touch with people. Oh, Rahomo, hello there, welcome back. Welcome to this current live stream. Just for the information, Rahomo, I'm about to finish the live stream, so just that you know, I'm just finishing this last for loop here. But nice to see you again in this live stream. And yeah, I don't know when I will continue, but I'm still working on the full system, by the way. And there's still a lot of work to do here. So yeah, I'm biting through it. How's it coming along? Well, slowly, but steadily. It is not finished yet, by far, but it is coming along, yeah. Thanks for asking. Residuals, add position I. There we have for a residual, we have the state again, which should be equal to res state to the object, and then in, which is probably a short form for in layer. But yeah, we do not know until we have implemented that. Okay, here we have a shared pointer frame hashen. For the host, we get the host by taking the point, then the feature, then the host.log, and then from that we take the frame hashen. So we are basically moving from the point. I think the point is a, yeah, it's really a point class. Then we have the feature class, then we have the host class, which is, I think, of type frame. Then we have the frame hashen. And what do we have in the frame hashen? Oh, that's it. Okay. So we store the frame hashen here. Okay, and there are many of those classes that we still need to implement. And yeah, I'm starting to get worried if I ever get this done in my lifetime. But yeah, if I talk, then probably never. So let's continue. Frame hashen. If we have the host, then we also need the target frame. And this is extracted from the residuals at index I, then target.log. And we have a shared pointer for the point frame residual. So we have in the hashen matrix, we have those blocks, if you know them, where we have like this part about points. I could pull it up, but I will just finish that. But it's in the paper for the direct sparse odometry. You can see the hashen there, and then you can see that, well, we have this point part, we have the pose part, and or the frame part, and then we have the point frame part, the off diagonals usually. And this is, I think, what we are doing here. So we are creating a new point frame residual for the first time. I see this for the first time in the whole code. We pass the point P, we pass the host and the target. And that's it. So now we update the residual. So we say R state new energy is equal to R state energy, and this is equal to 0. So we initialize with 0. Oops. Then we have the R state new state, which is equal to res state outlier. Then we have R set state res state in. And then we have P. I will put that in a new line. P and then residuals dot push back, and we push back the R that we have created. Okay, lastly there's a check if the target is equal to frames.back and then frames.back and then the frame Hessian. So target is a frame Hessian. Yes, a shared pointer to a frame Hessian. And frames.back frame Hessian is also one. So if this is true, so if our target frame is the last frame in our memory, then we want to set P last residuals at position 0 dot first equal to the residual R, and we also want to set the second with res state in, which is probably meaning inlier again, and else if the target is equal to frames.size is less than 2. This is, I think, a ternary operator, so we check if the size is less than 2. If this is true, then we return a null pointer, else we return frames at position frames.size minus 2. And from that, we get a frame, and we want to get the frame Hessian okay, and this is the check. And what do we do here? So if our target frame is the second to last, I think it means frame size -1 and -2. Then we want to do a similar thing like here. But here we want to set the index 1 for the last residuals. First is equal to R and second is equal to res state in. And this ends the else if block. This one else ends the if for the residual state. Okay, and here the for loop is being ended. And when we are at this point, we want to return P. And this, ladies and gentlemen, is how we optimize an imager point. This whole method here. Okay, with this, I would end the stream now. Thank you very much for watching. It was, again, a very interesting stream with getting to know new people and old people. Like, not old Rahomo, but people I already know from the previous stream. And this is nice to talk to people and code simultaneously. Like, simultaneously localizing and mapping. Yeah. Sorry I missed it. I'm glad you're streaming this. No worries. You do not have to excuse yourself. I mean, I will upload that to YouTube. So even if you say you want to watch me coding the next part of FullSystem.cc, you can watch it on YouTube. So no worries. It will be there once I get to it to upload it. Yeah, and next time you might be online as well for the live stream. So once again, thank you very much. I will now end the stream. See you next time, hopefully. If you're interested, I appreciate it. And yeah, have a great day, night, or morning, whatever it is on your side. Goodbye. See you. Thanks.